Hello everyone, and welcome to today's talk, Audio Signal Processing in MATLAB. My name is Yusuf Abdullah. I'm the product manager here with the Signal Processing and Communication Product Marketing team with MathWorks. In this session, I'm going to show a framework for developing audio processing algorithms in MATLAB using DSP System Toolbox. In this webinar, I will discuss real-time streaming and show you how to create this bench for audio signal processing using DSP System Toolbox in MATLAB. Secondly, I will show you how to develop a real-time DSP algorithms in MATLAB and incorporate them in your test bench. Lastly, I will tell you how to speed up your simulation using C and C++ code generation for real-time performance. To help with my presentation, I'll be using two examples, the Tunable parameter equalizer and the dynamic range audio expander. These two examples are part of the digital audio effects algorithms. Audio stream processing is everywhere. This mega trend is all around us. All you have to do is look at your smartphone, MP3 player, your audio navigation system in your car, or medical devices such as hearing aids. I'm going to start by showing you up front a tunable audio parameter equalizer example. This will give you a flavor of what you're going to see today. I'm going to stream the audio from a music file as a guitar tune that a colleague of mine from MathWorks has recorded while playing his guitar. I will use this user interface to tune my parameter equalizer filter. The parameter equalizer filters are a specialized audio filter that allow you to tune your specific filter parameters such as the center frequency, the bandwidth, and the gain in order to boost or cut specific frequency. So you can obtain a sound effect that you desire. So what you will see, I will play that piece of music. I will use the user interface to tune my parameter equalizer, and then I will display the overall effect using my time scope. And then we hear the effect using the speaker from my laptop. Let's switch to MATLAB and run this example. Here's my script, which I will be using throughout this presentation. All right, let me run script. Here's my spectrum analyzer, showing the response of each filter and the overall response of the parameter equalizer. So I'll be tuning each filter at a time and observing the response and the combined response of the three concatenated parameter equalizer. Increasing the gain. And let's see, I want to cut the bass. You get the idea that as we tune these parameters, we can cut or boost some of the specific frequency. So this is how the parameter equalizers work. Okay, let's switch to the presentation. We frequently talk to our customers and we hear from them some of the challenges they face when designing the audio system. They say they need a real-time simulation. They like to process large data and test this simulation with streaming signal. And other channels, they want a quick innovation in modeling. What they need is to find an innovative algorithm so they can create and model their working audio system very quickly. Another challenge is that as the algorithm get complicated and the system get complicated, their simulation slows down, and you want the ability to speed up the MATLAB algorithms. So what does DSP System Toolbox offers in MATLAB? Well, for the real-time simulation, we offer stream processing techniques and easy peripheral access that can speed up simulation and reduce memory footprint. For quick innovation and modeling, we have a library of over 300 predefined algorithms in functions and system objects that help you do quick prototyping. For rapid prototyping and simulation acceleration, the library supports C and C+ code generation that can enable the design continuity and faster simulations. Let's start with part 1, where I will show you how to create a real-time streaming audio processing test bench and how easy to connect to hardware peripheral using the existing audio cards on your laptop with DSP System Toolbox. But first, let us talk about streaming in MATLAB. What is streaming? When you are working with large data sets or continuous live data where all of the data is not available at once, you need to process the data in few samples or blocks of data called frames one at a time. Streaming techniques process the continuous data by dividing into frames and fully process each frame before the next one arrives. A key benefit is memory efficiency, which results in a smaller memory footprint. Let us run this animation, which will illustrate the streaming techniques. As you can see, the streaming data from the stream source is divided into frames and processed one at a time. The DSP System Toolbox provide implicit data buffering, state management, and indexing, which help in speeding up the simulation by reducing the overhead. If you want to learn more about the stream processing in MATLAB, please visit the link below that discusses stream processing in detail. Let me show you how to create a streaming test bench. Here's a block diagram of a streaming test bench where I use 3 components. A microphone to acquire my audio via the sound card on my laptop, where I can speak to it and stream the data, and a spectrum analyzer component to view the spectrum of the acquired signal, and a speaker to hear the acquired streaming sound. Let me go to MATLAB and show you how easy to create one of these components, and also give you a brief introductory to the DSP System Toolbox. At the MATLAB prompt, if you have DSP System Toolbox installed on top of MATLAB, all you have to do, type dsp.tab, and you'll see a library of components that we call system objects that are available to you and ready to use. I am trying to create a microphone component or a system object, so I need to invoke the audio recorder, dsp.audio recorder. Let's call the component or system object mic for microphone equal DSP audio recorder. And you can see I've just created a default component with the following properties that I can adjust and modify. So let's see, for example, how you can change the sound card to a different device. If I have other sound card installed in my laptop, what you have to do is type mic dot device name equal, then hit the tab key, and this shows all the list. Unfortunately, I only have the default sound card, but if you have other components installed, they'll show in this list. Okay, so we'll keep the default card. And other property you can change, for example, as sampling rate. Since I'll be recording, for example, my voice, you have to do type mic dot sample rate equal 8,000, and you can see I've just changed the sampling rate. I can also change the sample per frame if I want to. So all I have to do is mic.sample. Tab key gives you all the property you can change available to the component you created. So for example, I can make it 2048. And there you have it. You could see my sample per frame. I've just changed 2048. So how do you acquire the data? Let's create a variable called frame. To acquire the data, all you have to do is call the function called step of the mic. And I just acquire my first frame of 2048 samples. You see two columns. Each column represents each channel that I have acquired. Since I have a stereo sound card, so I would have two channels. If I call step again, I have the second frame. You can see the value is changing. And here's the third frame. Let me show you the value of the frame. You can see here the 2048 by 2, which means I have a frame of 2048 samples per frame by 2 channels. You can see every time I call another frame to process, again and again, the memory footprint has not changed, has not increased or reduced. This is the efficiency that we talked about earlier with stream processing technique using DSP System Toolbox. If you want to learn more about the DSP System Toolbox, all you have to do is type doc DSP, and it brings up the documentation, and you can scroll and look at all the different algorithms and tools that DSP System Toolbox offers. Now let us go back to the slide and continue our presentations. So how do you create this bench in MATLAB? And I'm going to show you a code snippet to highlight in detail how you do that. First, as I showed you, you can create a component by calling DSP dot. And the first step is you create it, initialize it with the proper properties. So you call, if you want to create a microphone, all you have to do is microphone equal DSP.audio recorder. And in this example, I also want a spectrum analyzer to view the spectrum of the capture audio stream. So I call DSP.spectrum analyzer. And to do stream processing, all you have to do is create this while loop where, as I showed you earlier, to capture each frame at a time, you call the function step. So you step to the microphone to capture the audio stream, and you call the second step to the spectra to view that frame you just acquired. And then finally, you just release this component for cleanup. So what you have is 3 steps. You initialize your components, you create it and initialize it, and then you do process in the loop. Sometimes we call it MATLAB in a loop, by capturing each frame and process it 1 frame at a time. And then you terminate by cleaning it up. Okay, let us go to MATLAB, to our script, and show you how to create all these 3 test benches, starting with the sine wave test bench. Let's run this part of the script. So as you can see my sine test bench, by now you see the initialization step. I have some properties that I want to initialize my component when I create it. The sample per frame at 100 and sampling frequency 44/100. So I'm going to create my system object or component called my sine wave by calling DSP.sineWave. What you will see is 2 separate sine wave, each with different amplitude. The first one is 2.5 and the second one is 3.5, and also different phase offset, 0 and pi/3, and each one have separate frequency. The first one is 800 Hz and the second one is 1000. Then I've created another component system object called my timescope by calling DSP.timescope with the following properties so I can display the signals. So let's run this section. You can run in advance 1 section at a time. So I've just created these components. You could see them right here. Here's my sine wave system object, my timescope, and these are the parameters that I initialize. Let me go back to the script here. And this is where the loop goes, the stream processing loop. that we call process in a loop, but I don't have a while loop yet. I want to step to this manually so I can highlight a few points. So if you see, I'm going to create a variable x to capture each frame at a time and then display that frame on my time scope. As I highlighted earlier, the way you capture frames, you call the function step, and you step through, in this example, my sine wave to capture a frame of 100 samples. So let's run this section here. See, I just basically capture my first frame of 100 samples per frame. You could see the blue sine wave has the amplitude 3.5 and a frequency of 1000 hertz, and the second one an amplitude of 2.5 and a frequency of 800, and you have different offset. Let's capture the second frame. Let me first duck the scope so you could see it as I run this section here. So let's run it again. Here's the second frame, and since I'm displaying 2 frames, so you could see 2 frames on my scope. And let's run it again. Here's the third frame and fourth frame and so forth. Okay, how do you create that stream processing loop or process in a loop? That sometimes we call MATLAB in loop. All you have to do is add the while loop. So let's say I want to run the loop for 30 seconds. Let's use tick, which is a timing parameter, and while talk is less than 30 seconds, run the following. And here's the loop. Let me save it, and let's run the section here. So I'm looping for 30 seconds right here. Let me bring up the time scope and say one word or two. This software time scope part of the DSP System Toolbox has the feel of a commercial industrial time scope. So you can basically get some statistic and measurements. You could look at peak and many other measurements. Okay, now that you have seen how to create a sine wave test bench, let me show you the second test bench and how to create a real-time test bench to import your live audio data into MATLAB from a microphone. Let's run this part of the script. So we're going to run in advance. And here's my audio and test bench. By now you recognize the initialization step where I create a different component and initialize them. So let's run this section. What I've just done right now, I created a system object called microphone, and you can see if we hover over it, here's all the property. This is connected to the default sound card and have sampling rate 44.100, and we're going to process or capture first a frame of 1024 samples per frame. Okay, and my second component system object is called spectra, which is basically I've just created a spectrum analyzer component, a system object, to display the spectrum of the capture audio. Now let me run the process in a loop to do stream processing, or what we call MATLAB in a loop, which is highlighted by this while loop. The first thing we'll do is we'll capture 1 frame at a time using the microphone connected to the sound card, and then we'll display that frame on the spectrum analyzer. Okay, let's run this section of the code, and here's my spectrum analyzer of my voice. Hello everybody, and this is what the spectrum of my voice looks like as I capture 1 frame at a time and display it on my spectrum analyzer. So I have just shown you a 20-second of streaming data as I capture 1 frame at a time and display it using the spectrum analyzer in the DSP System Toolbox. Okay, now all we have to do is exit and run the terminate part of the code. Okay, so all right, so let's close this test bench and go back to our scripts. Now that you have created a real-time test bench by importing or acquiring live audio to the microphone via the sound card, let us show you the final and third test bench This is a real-time test bench by reading an audio file that was recorded. And again, similarly, you stream the data from the file and process one frame at a time. All right, let us run the script. Here's the audio file test bench. Again, things that are looking familiar. We have the initialization phase where we create system objects and initialize them. So we're creating a file reader called fReader, where we're gonna read the file and process one frame at a time. The frame will have 1024 samples, and we'll read off the sampling frequency of the file reader so we can synchronize with it as we process the data. Here's our time scope system object that we created initializing by calling the DSP time scope. And here's a player system object that we created so we can play back the audio. And we have a fWriter, which is basically a file writer system object that we created by calling DSP.audio file writer. And we have set up the output file to be to record in MP4, which is MP4 format. And here's our stream processing loop, where we go into the while loop, where we read one frame at a time from the file reader. And then we have a trivial algorithm here where we attenuate the input audio signal by 80%. And then we take the output and input and view it on a time scope. So we'll be seeing the audio input signal and the attenuated version of that audio signal on the scope at the same time. And then the resulting audio will play back, and we'll hear them through the speakers. And then the attenuated audio as well, we'll save it into a file that we showed you earlier in different file format. All right, so let's run this test bench. So the time scope will show both the audio in and the attenuated audio. Okay, let me, here's the file that, here's the output in MP4 format that we converted. This is the file that we have initiated where we can write the attenuated and different format audio output. So let's play this file outside MATLAB using Media Player. So what you're hearing now is Media Player playing the attenuated original guitar sound in different format, MP4 format. Okay. Now that you have seen how easy to create various test benches, in this part 2 of the talk, I will show you how to develop algorithms and incorporate them with the test benches. In this first example, I will show you the dynamic audio expander. Audio expander is an audio signal processing device that basically used to increase the dynamic range of any audio signal that passes through it. The audio expander basically enhances the quality of audio signals by removing that low noise sound when recording your music. They are used for recording and remastering audio signals or old tapes. Let me explain how the audio expander algorithm works. Basically, the incoming audio signal levels are monitored by measuring the envelope of the signal, and this is done by the level measurement block. The output control signal out of that block is fed into the nonlinear gain processor, which in turn will apply a gain downward whenever the signal level goes below certain threshold. But before applying this gain to the input signal, it must be smoothed out through a low-pass filter. This process results in an expanded dynamic range, let's say from a level A to a higher level B. So before I switch to MATLAB and show you and run this example, first I need to design this low-pass filter. So I highly recommend that you visit the Digital Filter Design Made Easy webinar, which goes into the in and out of how to use the DSP System Toolbox to design various filters for your application. Okay, let's switch to MATLAB. In here, we'll step through I will run my script, and I want to design that low-pass filter, which I'm going to incorporate into my audio expander algorithm. In order to do that, you can call the filter builder tools from the command prompt. You can just run that command, and what you see is a user interface that will allow you to select the response you want to design. Or you could go to the apps gallery if you have the DSP System Toolbox and call filter builder, and you get the same user interface. So for my application, I want to design a low-pass filter. So I highlight that, and in this user interface, I would input my frequency specification to design this filter. So what I want is an FIR filter, minimum order, and a single rate, and I want the frequency in hertz, the passband frequency 4,750, and stop band frequency to be 5,250 hertz, and my sampling frequency to be 44,100. In terms of passband ripple, I want a 0.5 dB and a stop band attenuation of 80 dB, and I want an equiripple. And by the way, I can create a component system object directly from my design. Let's apply that. And you can see I have just created my HLP DSP.FIR filter. Let me look at the response of this filter. What you see in red are the masks that matches the specification. This is my magnetic response of my FIR filter. I can look at the phase response. I can look at the impulse response. I can look at the pulse zero plot. But more importantly, I can look at all the filter information. In here, I can see my design specifications. I can also see the measured. And here's something that is very useful when implementing your filter into a DSP or some ARM processor or FPGA. You want to know the cost to implement that filter. So it shows you how many MAC it takes to implement such filters. So you can go back and redesign it to meet your design criteria. Okay, let me close this. Okay, what I actually want is to generate code, a MATLAB code that I can incorporate in my algorithm. So all you have to do is generate a function that returns your filter as output. Let's click Generate MATLAB Code. Let's call it my filter. And here's that MATLAB code which shows the specification of the filter. I designed my filter, and then here's my system object that I created. I'm going to show you how I cut and paste this code into my expander algorithm. Let me show you in the script where I've created that or cut and paste that code. Let me run the dynamic range expander. Here's my function test bench, where you could see, let me bring this up, you can see in the initialization step where I created my component system object microphone, so I can capture the audio to the microphone one frame at a time by calling DSP audio recorder, a time scope component system object by calling DSP time scope, and a spectra system object calling DSP spectrum analyzer. Here are my design specifications for the filter And here's the code that I cut and paste from my filter. The only thing I've done is I've changed the name to FIR for that component system object. Here's my stream processing loop, where in this while loop, I step to the microphone to capture one frame at a time of audio. As I speak into the microphone, I display the spectra on my spectrum analyzer of the captured audio input, and then I call in my algorithm, the dynamic range expansion, which I'll show you the code, where I take the audio input and then I monitor the threshold of the envelope. When it drops below a certain level, my gain processor lower that signal to even lower level and smooth out that gain before it applies it to the input audio signal. And then I will show you by calling step to my time scope both the input audio signal and the expanded signal. Okay, before I run it and see how it works, let me show you the expander code algorithm. Here's my function expander, where basically I go to the envelope detection, and then I look in the gain processor. If the level dropped below a certain threshold, then I apply my gain by calling a step function, and I smooth that gain to the low pass filter before I apply it out to the signal. Okay, let me run the expander example. What you will see is the spectrum of my voice in the spectrum analyzer, and then in the time scope you could see in the blue the original audio signal and the green the expanded signal. Hello everyone. Hello everybody, and welcome to the audio signal processing. Okay, you could see here if I zoom out the level that's been expanded, especially talking about the lower level. You can see the original audio signal in blue and expanded signal in green. By lowering this noisy level here to even lower level in green, you could see that we had just removed this noise by expanding this range downward. Okay, now that we've seen how the audio expander works, let me go back to the slides, show you a code snippet that goes over how to incorporate the algorithm to test bench, as I have shown you in the code in MATLAB. So in the initialization step, as we know by now, you create the components that you need and use in your test bench. In this example, we created a microphone by a component to a system object by calling DSP audio recorder, and a time scope by calling DSP.timescope. And we do the stream processing loop, our process in a loop, or MATLAB in a loop. In this while loop, we capture one frame at a time by calling the step function of the microphone system object, and we will be displaying the result on a time scope by calling step my time scope. If in this example of the audio expander we needed extra parameters or create different components, we're going to design a filter component called FIR, and I've shown you how to design it. So the initialization and creation goes in this initialization step, and your algorithm will go into the stream processing loop right here. So you could see here I'm calling the expander algorithm, where I process the input signal and expand the range based on the threshold level detected. And when done, we just exit. Now, in this example 2, I'll be showing you the tunable audio parameter equalizer. Parameter equalizer filters are special kind of filters where they will, when they're tuned, you tune them to boost or cut certain frequency bands. A parameter equalizer filter normally are frequency bands that are concatenated together, so you will have multiple parameter equalizer. In this example of our parameter equalizer filter, I have 2 of them concatenated in series, and each one of them is tuned independently. You can see, using my user interface, the first set of parameters that will be tuning the first parameter equalizer. I can tune the gain, the bandwidth and center frequency, similarly for the second one, and the ratio of the center frequency bandwidth is called the Q factor of the filter. the way underneath the hood, between the way we tune the parameter and communicate those values to the parameter equalizer filters, is using a UDP component of system object to establish that connection to transfer those parameters and tune the filters in real time. In this example, we'll be playing that audio input, which is the recorded guitar tune that we heard earlier. And we feed that through the parameter equalizer, and I will be tuning the parameter equalizer, highlighting certain frequencies by boosting them or cutting them. And the output of the equalizer will pass it to the speakers to hear the effect of the filter on the audio input. And I have a additional component, is transfer function estimator, where I estimate the overall parameter equalizer filter response and display that response in real time on the scope as I tune those parameters and boost or cut those frequencies. So let's go to MATLAB and let me show you this example and show you some key algorithms. Here's our MATLAB script. So let me run the audio parameter equalizer test bench function. So let's run advanced. This open the audio parameter equalizer test bench function. You could see here's our initialization phase. I'm creating a file reader by calling DSP audio file reader, which creates the system object F reader by loading the guitar audio file. And then I am creating a transfer function estimate component of the system object by calling DSP transfer function estimator system object. This is the block that I showed you earlier, which will compute an estimate of the transfer function output of the overall tune parameter equalizer. And then I have a special time scope called array plot, where I will display 1 frame at a time of the estimated transfer function of the parameter equalizer filter. And then I created this speaker system object by calling DSP audio player, so we can hear the effect of the parameter equalizer when I tune those key parameter and pass the audio input to the filters. And I have some extra parameter initialization here for my user interface. Okay, and here's our stream processing loop. So you could see here our familiar while loop. I go to the loop, and here where my audio algorithm goes. So I pass the audio input with the tune parameter into the parameter equalizer algorithm, and the change or the effect on that audio input will be observed on the audio output, which then I will feed in the audio input into the transfer function with the audio output, and I'll be computing the transfer function, which is nothing but y over x, where y is the audio output and x is the audio in, and I get the h, which is our transfer function. So let me go to the algorithm and show you the audio parameter equalizer. Here's the audio algorithm parameter equalizer function. You can see in this function I've created the first parameter equalizer system object or component by calling the parameter equalizer filter. And you can see I step through the first parameter equalizer filter, the input, I get the output, then I feed that back into the second parameter equalizer. You can see they are concatenated in series. Okay. Now let's go back to the test bench and let me run the algorithm and see how it works. So let's run. Here's this transfer function estimate of the current parameter equalizer. These are the default value. I'll be tuning, and you'll see the transfer function estimating the overall parameter equalizer as I tune the parameters. I'm gonna highlight the gain of the first one. let's see, I want to highlight the base. Now you can see I'm cutting the base range, base frequency. Let me boost it. You can see the transfer function is giving me the estimate in real time of the overall tune parameter equalizer. Let me highlight another frequency, maybe in the mid-range. Let me increase the bandwidth of that. And adjust the gain. Cut the bass in this guitar imported file. So you get the idea. So here is the overall transfer function estimate of that tune parameter equalizer, and it's done in real time. Okay, now that we've seen the parameter equalizer and the transfer function estimate example, let's go back to the slide. And let me show you how to create that algorithm incorporating your test bench. So by now you're familiar with the 3 steps. We go to the create initialize step. And I'm only highlighting the new components. You're familiar with the other one, the file reader and the speaker. We have 2 new components here. The transfer func estimate system object that I created initialized by :DSP.transferFunctionEstimate, and my array plot component system object that I created initialized by :DSP.arrayPlot. And then we go to the stream process in the loop, where you're familiar by now. In the while loop, we step to the file reader to read 1 frame at a time into audio N, and then we do some sort of processing, and we call the array plot to show the signals, and call the speaker to play the sound. The algorithm goes right inside the loop. That's where we add the algorithm that we design. In this example, we have the parameter equalizer, which we call audio algorithm parameter equalizer, where we process the audio input and we tune certain parameters to cut or boost certain frequency range. And the output, we use those 2 input and output from the audio parameter equalizer to estimate the overall transfer function of that algorithm by calling again step transfer function estimate, so we can get an estimate of the overall filter response. And when we're done, we just exit out. The DSP System Toolbox has many components specialized for audio signal processing. The one marked in red as the one that we highlighted in these examples presented in this presentation. However, there are others such as multi-channel audio I/O. What I mean by that is 3 channels or more where you can acquire data in real time, just like we've shown with the sound audio card. And you can map those channels, and you have control over how you want to map them. Other things that we didn't mention that I'd like to highlight is such as MIDI connectivity, where we have MIDI surface control. You can use that to control the slider in your user interface and tune your parameter equalizer. So you can do them both via MIDI surface control or the slider. In this part 3 and final part, I would explain how to speed up your MATLAB simulation using C and C++ code generation. Before we talk about speeding up your MATLAB simulation, let's discuss real-time processing in general. So earlier we discussed stream processing, where we process large data. We divide it frame at a time, and we process each frame fully before we process the next one. So there is some time spent in acquiring the data. There's an overhead, and there's also an overhead or time spent in processing that data using the algorithm we designed. So as long as the time spent in acquiring the data plus the time spent in using one of those algorithms to process the data is less than frame time, then we have real-time signal processing. When these algorithms become more complicated, the time spent to process the data can exceed the time frame, and when it does, we no longer have real-time processing. What do we have in MATLAB? What kind of tools do we have that can help speed up the simulation in order to maintain frame time? There are many different ways to speed up the execution of your MATLAB algorithms. Many internal operations have built-in functions that are optimized to run at compiled speed natively, and in some cases even take advantage of the type of processor-specific optimization you have on your laptop or desktop. One option you have is, first, you can optimize your MATLAB code to take advantage of these specific performance improvements by using a technique called pre-allocation and vectorization. Second option that you have, if you have a desktop or a laptop with multi-core processor, or you have access to a cluster of computers, you can use parallel computing product to distribute your algorithm across different cores and PCs. That's another option to speed up your MATLAB algorithms. Another option is system objects, which you heard me introduce them in this webinar. I call them component or system object. And they're using my example of developing the algorithms that I showed earlier. They are highly efficient object-oriented implementation of the algorithms in the DSP System Toolbox. Those signal processing algorithms very well optimized using system objects. The automatically managed state information, data indexing and buffering for streaming signal processing. These are not only available in the DSP System Toolbox, in all the system toolbox, such as Communication System Toolbox or Phase Array System Toolbox, support system object algorithms. And many of them are actually pre-compiled to provide you a fast execution compared to the regular MATLAB function in most of the instances. If you tried all of the above options and still need better performance, instead of manually translating your MATLAB code to C, you can actually use the MATLAB coder product to automatically generate mix functions that are compiled implementation of your MATLAB algorithm, which you can run back in MATLAB. So once you generate your algorithm using MATLAB coder generate mix file, you can execute that from your MATLAB script, and then you should see some performance. And I have actually done that, and I'm going to share with you some of the benchmark that I've done for some of the algorithm in this webinar. But before I discuss that, I highly recommend the webinar listed below. It discusses all these options in detail. So if you want to learn more how to speed up your algorithms in MATLAB using these options in very detail, visit the webinar below. As I mentioned earlier, one of the options that is available if you have the MATLAB coder product, you can take your MATLAB algorithm as a function of system objects and create a C code. In this instance, what I've done is I've took the parametric equalizer algorithm and I converted to a mix file so can benchmark how much acceleration I would achieve. In this link below, there's a webinar called Design and Prototype for Real-Time DSP System with MATLAB. This is a conference presentation that a colleague and myself has given back in March, where it highlights multi-channel audio, and we show how in detail how to use the MATLAB coder to achieve speed up in your simulation. For my benchmarking, I took the two-band parametric equalizer algorithm and I generated a mixed version of the MATLAB code, And then I ran both and looked at the processing time it took each one of them to execute. And here's the data I obtained. For the MATLAB code, it took me about 24 seconds. On the other hand, when I mixed code the same algorithm, it took me only 3 seconds. That tells you it's about speed up of 8 times. The DSP System Toolbox has over 300 algorithms that can help you model, design, implement, and deploy any dynamic system application, such as audio application. They have advanced filter design, adaptive multi-stage and multi-rate filters. The visualization tools such as the time scope and frequency domain, they're very useful compared to the your typical industrial or commercial scope and frequency domain. All the knobs and that you have for measurement and instrumentation, we have similar measurements on the scopes that we have, and they are very useful when you're trying to debug your code, or you try to visualize, like I showed earlier in the examples here, the signals that you are processing. Furthermore, it offers support for fixed point, and most of the algorithm, either system object, support C and C++ code generation, and also offers support for ARM Cortex-M if you want to do PIL or hardware prototyping. Please visit the DSP System Toolbox product page to learn more about the product, and if you wish to download a trial. In conclusion, we have just presented a framework for audio processing in real time, presented by the following workflow, where we show you how to create this bench for audio algorithms with various sources and sinks. We showed how to do streaming technique for real-time audio processing, and how easy to access different audio peripheral hardware with multi-channels. Then we show how you can use the DSP System Toolbox component that we call System Object to develop your algorithm. And finally, we showed you how you can give you different options, how you can speed up your simulation, more specifically when you generate a mix function using the MATLAB Coder toolbox. Thank you and have a nice day.